It turns out that the equations of electromagnetism, Maxwell's equations, are, how do I want to say this without me having much of the context? They are invariant, which is basically another way of saying that they behave the same way in different reference frames. They're invariant if they undergo space-time transformations that turn out to be what's called Lorentz transformations. It's a little bit hard for me to say this without leaping forward into next week and next semester. These Lorentz transformations are types of coordinate transformations that turn out to be relevant for special relativity. So they're not Galilean transformations in the sense that we've dealt with this semester. They're different. So it turns out electromagnetism is invariant under Lorentz transformations. And Einstein, as part of his thinking about things like the apparent equivalence of gravitational mass and inertial mass, and then thinking about how transformations in mechanics might be made more consistent with those in electromagnetism, Einstein basically says we're going to try applying these new Lorentz transformations to mechanics as well, and this is what gives rise to special relativity, about 12 years before general relativity. So Einstein's working on all of this stuff, realizes that gravitation with special relativity doesn't fit, and as he sorts of thinks about these discrepancies, comes up with general relativity. All right, so I'm trying to race here because I know I'm going to run out of time. This is all FYI, by the way. I'm not going to test you on any of this stuff. The answer that eventually Einstein comes up with is kind of the bottom bullet on this slide. And it's the idea that somehow acceleration or uniform acceleration and the influence of gravity or mass and energy in space are one and the same thing. In fact, the overriding idea, if I have to give you one that I kind of feel is the basis of general relativity, is that it's impossible to distinguish between uniform acceleration and gravity. So that's a really radical statement if you are looking at this from a classical physics perspective. Okay? Now, there's a lot to think about here, and Einstein's famous for his thought experiments, deeply thinking about these things. So this is just obviously glossing over the surface of many interesting ideas. All right, so another sort of aspect that I guess I would tie into this is we can define zero acceleration as basically being free motion in the presence of whatever gravitational field is around. Okay? So in a sense, we can imagine the sun as determining the motion of a free-falling Earth, and then see what sort of picture of the universe or the world that gives to us. All right, again, a lot of stuff here that is look forward, but I hope it's not confusing. I hope it's sort of slightly enticing and interesting. So ultimately, the way to maybe re-envision gravity is it's not so much a force, but it's instead a change in the underlying space. And I keep saying space and then saying space-time. We have to wait till next week to understand why that's true. But let me just say for now, it's a way of thinking that space is curved by mass or energy. And mass and energy equivalence we'll talk about next week when we talk about special relativity. So the middle of this slide somewhere, it says that objects try to follow the straightest possible line as they move through space-time. And if that space-time is itself curved by the presence of mass or energy, then those straight lines don't look to us from our Cartesian geometry perspective as straight. They look like curved paths. Technically, how this is described is a little bit beyond the scope of what we're going to cover in intro physics, but for those of you who are going on to do more physics, some phrases to keep in the back of your mind. These trajectories are defined as paths of least action. That's a very powerful principle in an energy-based formulation of mechanics, so-called Lagrangian mechanics. So some of you are going on to do more physics will learn a lot about this in more advanced mechanics courses. Bottom line of all of this is that these so-called straight line or least action trajectories are no longer straight in a Cartesian sense, but they are typically going around in circles. And if I have time at the end of class today, I'll raise the light level again and show you a representation of this with that demonstration that looks like a trampoline down at the front before we wrap up. All right, so let me move along. That's the demonstration I'm going to try and show you quickly at the end. That picture up top is the idea of, in 2 dimensions, that sort of horizontal membrane that seems to look like a spider web. If I put a mass in that membrane, remember this is representing 2-dimensional space, where the mass is, that 2-dimensional space gets curved or warped. So this is very much easily visualized by thinking of a mass on the surface of a trampoline. Keep in mind, of course, this is actually happening in 3 spatial dimensions when we talk about the space as a whole. And so this idea of straight lines, represented by that blue object there, is it's trying to follow a straight line in terms of a least action trajectory, but since the space itself is curved, the straight line actually is a curved orbit. Okay? So this is the sort of visual picture that underlies general relativity. Introduced formally, I always think of 1917 rather than 16, I'm not sure which is correct. But it turns out it's a hugely radical, and turns out almost instantly successful rewriting of how gravity is understood. What do I mean by instantly successful? I'm not going to talk about the math behind this, it's a little bit technical, but immediately explained this anomalous behavior of the orbits of planets in our solar system, Mercury in particular, and interestingly enough, it predicted a new phenomenon that was observed just a couple of years later. And it's the idea that since masses in space curve the space, then that cartoon I had on the previous slide, that blue path of a mass, because energy and mass turn out to be equivalent, this is Einstein's special relativity theory, then the same should be true for light, that it should in fact also get distorted as it moves through curved space-time. And if you set things up in a nice way, I'll hopefully have time to show you this, you can see that masses in space serve as effectively so-called gravitational lenses for light that is passing behind it. And so I'll talk about that a little bit more in just a moment. But this bending of light due to mass was in fact observed in 1919 in a famous expedition to go and look at a solar eclipse. General relativity had just come out. Einstein had this prediction that you would see a slight different behavior if general relativity was true, in terms of the time duration of this eclipse compared to with Newtonian gravity. And it turned out at that time people were able to make sufficiently accurate measurements that it confirmed general relativity. So let me talk about a few other aspects of this. We've talked about the first one already, the idea that objects, and maybe even then mass, will move along curved trajectories in space-time that has mass or energy embedded in it. And then 2 other things, which I know I'm going to run out of time to talk about. The one that I want to spend most time on in the remaining 7 or 8 minutes is the idea of gravitational waves. I'm probably going to run out of time to talk about black holes. But if you think about it, since I'm going to run out of time to talk about black holes, let me just say what the punchline is right now. If you have a very large, very dense, massive object in a certain region of space, and we've introduced the idea that that curves the space-time around it, you could imagine that if you have a large enough mass and a dense enough mass in a certain region, it will be so powerful in terms of curving the space-time that it will actually, for any incoming light, it will capture it in a sense, and its path will be kind of wrapped up so tightly that it could never emerge again. So this is the idea that gave rise to the prediction of black holes. But there are objects in our universe that may exist, of course they haven't been detected at this time, that are so dense that they can trap even light within their gravitational influence. Eventually these became known as black holes. That took quite some time. They were originally called gravitational singularities, but a few decades later they became known as black holes. So a quick discussion more precisely of what gravitational lensing is. The middle cartoon there, or the one on the left of the 2, is again in 2 dimensions. What you should be looking at here is some light source up at the top. It's sending out light waves in all directions. The 2 in white happen to be 2 selected light waves that travel close to a mass that's somewhere in between the source and the observer. So imagine you as the observer, you're looking at light from a distant source. but in between you and the light from that distant source is a massive object. Okay? That massive object, as we've seen now, according to general relativity, warps the space-time around it, and as light passes near it, it's going to get deflected a little bit. And so if you follow those two white lines, think of them in the sort of geometrical optics perspective, where they're just simple straight lines. Those two white lines get lensed. It's very much like a lens in the optical sense. They get distorted, they get lensed, and they can be focused back to a point. If you set this thing up correctly, you can observe this lensing effect. What does it look like? The thing on the right is supposed to be a representation of what it looks like. Here's an observer on the Earth, a telescope on a mountaintop somewhere, looking at a distant radiating object. The light that we see, because of course when we look at light, we extrapolate and say that it came along a straight line. So what we see is those two white lines at the bottom, and we extrapolate them to those 2 points with the dashed lines far away. But in fact, that's light coming from a single object. And if you think about this in terms of a three-dimensional picture, it means you can, in principle, get multiple images of that distant object that seem to kind of form around a ring, okay? These turn out to be called Einstein rings, and we've been observing them for a long time in astronomy. Here's an example. This happens to be from the Hubble Space Telescope. So the image on the right is hopefully discernible roughly what it is. It's a bunch of galaxies far away. But you see, aside from things that look more or less like galaxies you're familiar with, you see a few kind of circular arcs or streaks. And these are, in fact, gravitationally lensed images of a very distant single galaxy far away, the light of which is coming towards us. As it comes towards us, it's being lensed by some intervening mass distribution and gives these sort of circular arcs. So these sort of Einstein rings we've been using quite a lot in recent decades to actually enable us to map out intervening mass distributions that may or may not be visible between us and the distant object, and allow us in particular to map out things like dark matter distributions in our universe. So, okay, let's talk a little bit about gravitational waves in the last 3 or 4 minutes. How do gravitational signals propagate? So remember, in Newtonian gravitation, we have no explanation for how that force is felt. We do know that according to special relativity, anything getting information cannot travel faster than the speed of light. And just as an interesting observation associated with that, as you know, the sun is about 150 million kilometers away from us. If we know the speed of light, which is roughly 300,000 kilometers per second, we can quickly calculate that light from the sun takes about 8 or 9 minutes to get to us here on Earth. So light takes time to propagate over distance. Well, since gravity presumably is subject to the laws of special relativity, the absolute fastest gravitational signals to be propagated is the speed of light. So in fact, if somebody suddenly took away the sun, we would not notice that either with light or with its gravitational influence for at least 8 or 9 minutes, okay? So gravitation, whatever it is, has to be transmitted in a way that is consistent with that limiting speed limit from the speed of light. Okay, possible different ways of thinking about this. We can think of it in terms of wave transfer of information. That's the thing I want to talk about just for a couple of minutes. Or possibly we can think of it as particle transmission of information. On Tuesday, somebody mentioned the word graviton. Possibly you can think of this as being transmitted by particles that are moving back and forth. If so, you might imagine that those particles are massless, like light particles, photons are, and that gravitation is transmitted, in fact, precisely at the speed of light because the graviton is massless. May or may not be true. There have been people, including people here in the department currently, who work on ideas that gravitons, if they exist, are not massless, but they have very small masses, in which case gravity would be transmitted slightly more slowly than the speed of light. In a wave picture, we can imagine that since gravity distorts space-time, if we jiggle masses around, then the distortions in space-time are also going to be jiggled. And this gives rise to the idea that we may be able to transmit gravitational waves through the universe. And the reason I particularly want to focus on this is because in the past 3 or 4 years, this has been discovered for the first time. It's a really, really big deal. So very quickly, bear with me, I'm going to try and finish just 2 minutes late. Imagine a couple of massive objects rotating around each other. Those are those 2 red objects there. Why would I do that? Well, first off, if this exists, and it turns out they do, they're very prevalent in the universe, if I have very dense, massive objects in close orbits like this, there's sufficiently strong gravitational forces that they could produce, relatively speaking, large gravitational waves. And one idea from general relativity is that if these things exist, those waves will propagate outwards, let's say roughly at the speed of light, and they'll propagate outwards in this cartoon analogy like sort of ripples on a 2-dimensional surface, like water ripples on a pond if you throw an object into it. Again, of course, this is truly in 3 dimensions. So we can imagine these rapidly moving massive objects as like gravitational wave transmitters. If they exist, and we've known now since 3 or 4 years ago that they do, they have a very interesting effect as they pass by. They have the effect of simultaneously compressing space in 1 dimension while expanding it in a perpendicular direction. And then as the wave passes and we go from a peak to a trough in a waveform, that compressing and expanding flips, and the orientation that was compressed in 1 instant expands in the next instant, and vice versa. So the whole of space can be imagined as waves passes as being distorted in this rather interesting way. So I'm going to skip right to this, skipping over some things that were not successful attempts to detect gravitational waves to the most recent one that has been. This is a state-of-the-art gravitational wave detector. It's actually 2, but part of the same project. It's called the Laser Interferometric Gravitational Wave Observatory, LIGO for short. We have people here at Columbia who've been actively involved in this. These are very large experiments. These are about 3-mile-long vacuum tunnels that have lasers, powerful lasers going back and forwards in them, bouncing off mirrors. And sadly, I'm out of time here. But it turns out if you set these things up as what's called an interferometer, which we'll talk about in the spring semester, you can be very sensitive to tiny, tiny displacements or changes in distance between objects. So what these things do is in fact measure with great precision the distance between pairs of mirrors that are separated by about 3 miles. And they happen to do it in perpendicular directions because that makes us particularly sensitive to gravitational waves passing. So, okay, this is what will happen in principle. So there's the simultaneous or sort of consecutive stretching and expanding in perpendicular directions as gravity wave passes. If you set up a laser interferometer like this and you look at those pink and blue things as being mirrors, if you can measure the changing distance between these things, you might in principle be able to detect gravitational waves passing. I want to give you an idea of how remarkable these experiments are. They are sensitive to changes in the separations of those mirrors. Again, they're separated by about 4 kilometers. They're sensitive to changes in the separation at the level of 10 to the minus 17 meters. Okay? That's 100th the size of an atomic nucleus. Totally amazing. Okay? All right, punchline. Back in 2015, gravitational waves were first detected in this experiment. Turned out they were gravitational waves emitted from a black hole binary pair that collided several billion years ago in a galaxy far, far away. So this is a huge deal. Huge deal. I don't have time to be excited about it, but it's the first time we've been able to detect gravitational waves directly. Since then, we've had several more gravitational wave detections, not just from black hole collisions, but from neutron star collisions, a huge amount of new physics coming out of this. All right, so you guys are getting restless. I don't have time to talk about black holes. All right, let me stop. Hold on. I'm going to post some of this on coursework, so if any of you want to learn more about general relativity and cool things about general relativity, come and talk to me, and then on the way out, come and play with this 2-dimensional representation of curving of space by atoms. Okay? I'll see you guys next week. Thank you.